I think it's time to move from the substation and protection world to the world of overhead lines. My name is Usama Ahmed. I'm the CTO for T&D Solutions for Shemar Group. This is a presentation about enhancing new build and existing transmission lines with composite insulated cross arms. I'll be co-presenting with my colleague James Deas from National Grid UK. Shemar Group is working with them on the RICA project, so he'll talk a little bit more about the RICA project later on. So a quick introduction about who Shemar is. We are active in the transmission and distribution space. We are providing advanced transmission line and grid enhancing solutions, and also composite insulation products for T&D industry. We have a big booth down at the end where you can see 400 kV insulated cross arms in action. So what is a composite insulated cross arm? Well, this is what it looks like. The idea is that you no longer use a steel lattice cross arm and a suspended insulator set, and you replace it with an insulated cross arm. So the insulated cross arm here is functioning as a mechanical support, holding on to the phase conductor, of course, providing adequate spacing between the phases, and it's also providing electrical insulation to the phase. It can be used in a new build application, or it can be retrofitted on existing transmission lines. So construction-wise, you've got a post insulator that is triangulated, sometimes a singular post insulator, and then a brace insulator. So it's an engineered application for composite insulators. So for new construction, the key value of using composite insulated cross arms is compaction. The idea is you replace or don't use the steel cross arms, and you use insulated cross arms to compact the steel structure, so you make it lighter. That has a trickle down effect that the foundations get lighter as well. You squeeze down the corridor and the right-of-way. So these are just some of the typical numbers, reduction numbers that you'll see in a typical project. We see a lot of European TSOs, for example, in Belgium, in UK, they are defaulting to a construction with composite insulated cross arm as a default because of the benefits that it brings. In addition to, of course, physical benefits, there are operational benefits that come with the use of compaction and insulated cross arms as well. So smaller footprint and right-of-ways. You can see side-by-side comparison here. This is from the CIGRE Green Book. Two 400 kV transmission lines side to side in Dubai, and just the sheer difference in their physical footprint and the space they occupy is self-evident. Scandinavian Nordic countries, even in Canada where I'm from, there is a lot of concerns about EMF from transmission lines as well. Compaction helps to bring down EMF as well, because when you compress the phases, you bring them closer to each other. It has a net cancelling effect on the EMF signature from the transmission line. And of course, these lighter transmission lines, smaller transmission lines, are more aesthetic as well. So they are not as ugly to look at compared to your lattice construction. So they integrate into the environment more easily as compared to lattice construction. In the US, brace line posts, as they are called over there, this is used heavily at 138 kV voltages, 230 kV voltages, and now increasingly at 345 kV voltages as well, primarily due to the cost advantage, because using insulated cross arms makes the transmission line construction much more modular and much more quicker, because for us in the US, for example, the cost of construction and labor is the primary component for upfront capital investment for any transmission line project. It is not the material, but in fact the construction and the labor that determines and dominates the cost of transmission line projects. So this is not a new concept, In fact, line compaction started on very early. So probably the first picture that you see here is from New York City, 1887. So this is a telecommunication line. So if you count, there are 12 wooden cross arms, over 500 pin insulators, on this structure. So the need for compaction really started early on. And then you can see in the transmission domain, all of these are from US because it started as an early adopter of these armless construction. 69 kV line with these porcelain line posts in Los Angeles, California. And then you can see the evolution of this concept. So you see a brace post at 138 kV. The idea is to include a porcelain post with a porcelain strut. And then you can see in the 1980s, this is where the polymeric and composite materials started to emerge. And very quickly, this concept was adapted to composite insulators. And the reason was that the material, FRP, is much more adaptable to cantilever applications. So porcelain is a brittle material. It's a binary material. It is not suitable to withstand bending loads. Whereas with FRP, composite insulators, they can withstand bending loads without being damaged. So this is I would say, the current portfolio or the menu that you have if you're looking for compact line solutions or armless constructions. So you've got line post insulators, brace posts, pivoting horizontal weaves, and then triangulated insulated cross arms. And really, from a functional standpoint, they are an insulated cross arm. They are fulfilling the definition that they are providing mechanical support and electrical insulation in an armless construction. The fundamental difference among them is mechanical loading, how much mechanical strength they can give in order to support the transmission conductors. So line posts are typically limited to 138 kV, brace posts 230 kV, and with these insulated cross arms, it is virtually limitless. So we've applied insulated cross arms to over 1000 kV transmission lines. So these can be designed for any line loads, 8 bundle conductors, 550 meter span lengths. There is no ceiling to what these can be designed to now. Some of the examples to basically depict what the state of the art now is. So you can see triangulated insulated cross arms on lattice construction. You can see insulated cross arm being applied to 1000 kV UHVAC lines. I'm talking about a section length of 11 meters here for these porcelain insulators. So these are humongous. So from this wall to this wall would be an 1100 kV post insulator. And what we also see now increasingly is these are no longer limited to suspension or tangent structures. So you can see on the far end, these are now being applied on dead end and tension applications, which means that you can use compaction and compacted designs on the whole route of the transmission line. So your tangents, your suspensions, your large angles, and also dead end applications. This is just a visual representation of what it means with triangulation of insulated cross arms. So again, a single brace post would have limited longitudinal capacity, whereas a triangulated insulated cross arm will give it more longitudinal capacity, so it can withstand broken wire conditions. It can withstand other security load conditions, which include unsymmetrical ice loading on transmission lines. I'll be talking here about greenfield because I'll leave the retrofit to Jimmy here. But again, to show you this technology in action, some of the projects that have been done in the world. This is an example from China, 220 kV. You can see the side-by-side comparison here. These two 220 kV transmission lines have been designed to the exact same parameters. And just with the virtue of using insulated cross arms, you can see the difference in the relative footprint of construction. So trickle down effect, right-of-way reduction in the amount of material and steel that you use, and that translates into cost savings, sustainability, and environment benefits. I'm sure you've seen this. This is the famous Steep Island, again from the UK. This was the first design iteration in the UK after hundreds of years of using pylon construction, and the idea was making transmission lines more aesthetic and more environment friendly and easier to integrate with the environment. Lastly, as I said, a lot of interesting work is going on as well as far as development. We are working with the European TSO right now, developing an insulated cross arm with a quad bundle dead end. So you can see the yoke of the insulated cross arm supporting a quad bundle dead end. Again, these are innovations that keep on happening to enable more sustainable and eco-friendly transmission lines. So I'll just present this and I'll leave it off to Jimmy. I'm keeping an eye on the time. So now we move on to the brownfield applications. As far as brownfield or retrofit applications is concerned, we can categorize them into three main, I would say, groups. So first of all, you retrofit an existing transmission line for voltage upgrade. This is an example from Pacific Corp, which is in California. They had an existing 230 kV transmission line that has been upgraded to 345 kV with the use of insulated cross arms. The other one is thermal upgrading. The idea is, again, to replace the bottom two cross arms, replace them with insulated cross arms. That lifts up the attachment point of the phase conductor, and then you can sag the conductor more. 500 kV application, 300 megawatt upgrade on existing transmission line. And then lastly, ground clearance mitigation. So in North America, there are a lot of NERC violations where we need to have adequate clearance to ground, and retrofitting with insulated cross arms, as you can see, helps to improve ground clearance, which is roughly equal to the length of the original insulated string. So Jimmy, I leave it to you now for the RECA project.
Thank you. So, the RECA project, the first thing I'll caveat this with is it's an ongoing live project. We're about halfway through. This hasn't got all the answers because some of the things we're still working through, but this is our findings so far. So in the UK, we have two suites of towers, L3 and L66, built in the 1950s, early 60s, operated at 275 kV. They've been reconducted, refurbished 2000 to 2015, and we're now looking at uprating them yet again to 400 kV using the CICA solution and all the benefits of increased ground clearance, using exactly the principles of you're getting back the height of your suspension insulator string effectively. Also, you haven't got the internal clearances and the ground clearances with a traditional. So at the moment, we're just looking at the suspension towers, and obviously you haven't got the swing angle anymore because you haven't got an articulated insulator string, and your conductors are now further up the tower. I'll leave that to explain itself. The only thing I would say is in some instances you can achieve a tower height reduction, but generally on the project we're working on at the moment, you actually have to increase the height of the tower because the earthwire shielding angle that you had when the conductors were on the suspension insulators, you've now brought the conductors higher, so you've taken them outside of that shielding angle. So you have to put a slight extension on the tower or come up with some other externally capped line arresters and other such like things. But generally, if you're doing a like for like, you would just have to raise the peak slightly to give you back your earthwire shielding angle and hence your reliability. And I think everything there speaks for itself. Ground clearance increase, voltage upgrade, so straight away you're looking at somewhere around 45% increase in load. Where should we go with this one? So essentially, we've come up so far with what I think is quite a nice solution in that we've got one single RICA design, which is for suspension towers alone, which is the double V solution, something similar to this. So your stock, your training, your maintenance, etc., you just have to worry about having one RICA, and there's obviously price advantages with that in terms of purchasing. And what you do is you change the attachment steelwork for the point on the tower, which is obviously cheap and cheerful by comparison. Again, looking at it, you could come up with lots of complicated maintenance procedures for changing this breaker, what have you. When you look at it for speed and efficiency, if you did have a problem, you wouldn't try and maintain that on the tower. You would just drop it off, pull the conductors to the tower body, drop the cross arm off and replace it. So your downtime and, again, your maintenance procedures are very much reduced. So on Tuesday, we completed a test line at our CIGRE training facility where we built a low height arrangement of 6 towers. We've only strung the top phase, and what we're doing there is now, as we speak, they better be, we'll be developing ways of maintaining, attaching all the procedures that you need as a full suite to maintain, install and operate your RICA route. This gives you just a bit of an idea. This is a terminal tower. This is tower number 1 of that route, and it's a DJT tower. That is tower number 2. Keep walking away. So again here, we'll be RICAing one side of these towers initially and demonstrating probably in October all the associated maintenance practices and refurbishment work that goes along with your now RICA installed route. And just in the background there you can see a full height, that's an L66 tower, and in the background there you've got an L3 full height tower here. I think that's about it for where we are. Come back in 2 years' time and we'll give you an update on how it all went.
Thank you, Jimmy. Thank you. Yeah.